Hello everyone, welcome. This is ECE317, the digital signal processing class. Last time we have studied the LTI system. We know that the output of an LTI system can be obtained by a convolution. The convolution of the input and the impulse response that give us the output. However, the convolution, sometimes to calculate a convolution by the definition is not so easy. You need a lot of calculation. So today we will introduce a kind of shortcut, some easy way to calculate. And actually the new method not only for the calculation of the convolution, this new method also provide us more tools on the study of LTI systems. That is a Fourier transform. Let's go to here. So today is a ECE317. The third week. This is Friday's class. Right? So we know for LTI system, suppose the system is S. This is a LTI system. When you give input x of n, you can have an output y of n. This y of n can be calculated by a convolution of input with the impulse response. Right? Input with the impulse response. But how to calculate this? We use the Fourier transform. This is a discrete time Fourier transform. The DTFT. So we will use this. Of course, before we can really apply it, we need to introduce what it is. We already have some discussion about the Fourier transform. Remember, the first one is for the DFT. So discrete Fourier transform. We start from some values of a signal x, like this. Then we can try to find the formula so that x of n equal to summation of some x of k times e to the j omega 0 n k kn. We put the n in the backside, and the k run from 0 to n minus 1. So we can try to write xn in a formula looks like this, where what is omega 0? Omega 0 is 2 pi over n times 2 pi over n. So this one, you see this part, frequency is omega 0 k, which is 2 pi over n times k. You can have I can show them in graph from 0 to 2 pi. Then you separate as n pieces, right? Divide by n. So this is 2 pi over n. Then k of it, k times of it, and the k run from 0 to n minus 1. So that means all this point. This is 2 pi over n times 2 until this will be 2 pi over n times n minus 1, right? So this is the that is formula. And actually the DTFT x of n, DFT will give us capital X of k. This is a method. Here that is but this I need 1 over n here. So if we calculate this coefficient by DFT. We cannot use it directly. We need to divide by n, put it here. Then we can have this formula. Alright. And what is this DFT? Then you need to check. I think I didn't introduce this last time. But I give you the chapter in the textbook. If you read that section, you should know this xk, how to get this xk. X capital K will equal to x of n times e to the negative j omega 0 kn, and here's n run from 0 to n minus 1. So we have this. This is DFT. Now we also have an example, right? To find this coefficient, then I can write any kind of signal, just have some values by a formula. Okay, now you look at here. You have n, right? You have n. What is this n? You have n observations, right? Now suppose you have all these values of x. You have all the values of x, not just finite values, not just n values. You have infinite values. The n go to infinite. You can also think this is a periodic signal, right? We suppose this is a one cycle of a periodic signal. If the period go to infinite, that means for all the n's, it is just one period. Okay, in that case, can we do the similar thing? I will say yes, right? Just n go to infinite. N go to infinite, then you have more point, right? More point. Every point you have a sinusoid. You have a periodic signal. This is sinusoid. This is a complex sinusoid, right? It's a cosine omega 0 k, the frequency times n plus j sine. The frequency is omega 0 k, then times time, right? It's this one. It's a sinusoid with omega 0 k as the frequency. Now n go to infinite. Omega 0 tend to be 0. Then the frequency, all this frequency, now it will cover the whole period, whole interval from 0 to 2 pi. Okay, that is the case. This is a DTFT. So DTFT, we have x of n. Now n run from negative infinite to positive infinite. We have all of these, and we will try to write x of n equal to similar with these, but now we have infinite terms. Now we have this infinite terms times 1 over n. I write it somewhere. I put it here. 1 over n times x of k. What is this? I put 2 pi. You see, you look at it here, right? I already say the frequency run from 0 to 2 pi. So I times 2 pi here. But then I need to divide by 2 pi. This is same thing, right? This is same thing with these. And n go to infinite. And you do a summation. Is this to remind you something? You have an interval, this is a 2 pi over n, and you have a value of capital X. This one times this one is what? This is the area, right? And you have a lot of this kind of area, right? Depending on the value of capital X, you the summation of all these areas, and let this interval, the length of the interval tend to 0 when n go to infinite, right? Tend to be 0. What is that? Oh, the area below this curve is what? I think you already know that, right? There will be integration. So this formula, in generally, if you know all these value, not just all this value, 0, n run from negative to positive infinite, then this part will become 1 over 2 pi integration from 0 to 2 pi, then capital X now it is not k, because you have infinite case. Somehow it's continuously from 0 to 2 pi, right? This is something from 0 to 2 pi. And here we'd like to use this notation. Yeah, this notation is somehow, if you just look at this, is not so natural, but later you will know e to the j omega, x of e to the j omega. Actually, this is a function changing according to omega. It's a function of omega, but we write in this way. And later we should know this notation can give us some convenience. Now you just remember we use this notation for these coefficients. And each one times e to the j. Now this is not omega 0. Omega 0 is a frequency, right? Frequency times n, and this is d omega, right? You will do summation for all these omega 0 case. Right? Summation along this is a omega 0 case, right? So that is omega. So do summation, do integration, integral according to omega, and omega run from 0 to 2 pi. So we have formula look like this. So we can represent x of n as I say is a combination of e to the j omega 0 n. No 0 omega, sorry, e to the j omega n, and omega run from 0 to 2 pi. Or you can use different cycle, so this is an angle, this is a frequency, right? So you can, or like a negative pi to positive pi, or even you want like a pi to 3 pi, or even you want to use some strange thing like pi over 3 to 2 pi plus pi over 3, so it's 7 pi over 3, even like this. Yeah, it works, doesn't matter, one cycle, 0 to 2 pi, one cycle. And most common use is this one and this one. In MATLAB, use this one. If you run MATLAB, they have a built-in function to calculate these kind of things, and the frequencies they run from 0 to 2 pi, 0 to 2 pi. And in our textbook, we use this one from negative pi to pi, because if we write as a formula, this kind of symmetrical, right? It looks better. So in the textbook, it is this one, and for MATLAB, it is a convenience for calculation, right? So the convenience for numerical calculation, so they use this one, but the same thing, yeah. So we try to write in this way. Then how to determine this x? Okay, we have a formula. Capital X of e to the j omega equal to summation of x of n times e to the negative j omega n, and n run from negative to positive infinite. And this formula is given by Fourier, so we call this a Fourier transform. We start from signal x of n by a Fourier transform. This is a Fourier transform, DTFT. Fourier transform, we get this one. And what is the meaning of this? This capital X gave us the weight of each component. Yeah, I said the weight. Remember what is the weight? You want to make a like a cake, right? You need some flour, some sugar, some milk, something else, right? Every component you need a certain kind of weight. Then mix all of these together, you get your cake. You get cake, bread or cake, whatever. Yeah, it depends. You need different weight, right? So we call this a weight. Yeah, but here in most cases we call this spectrum. Spectrum is a kind of coming from physics. When people study the light, we look at this light from the sun, it is a white color, right? But actually it is a mixture of different color. Some red, some blue, some orange, some yellow. Yeah, they have several different color mixed together. You get the sunlight, the white light. And that one we call it a spectrum. You separate as different light, different frequency, right? The the difference between different color, that means different on the frequency. So people also use this one, spectrum. We call this a spectrum. And this formula gives us a way to calculate based on the capital X to find the lowercase x, right? We have these, we want to go back. So we call this is the inverse Fourier transform. Inverse DTFT. So from DTFT, by DTFT we can find this capital X. They are the weights of each component. And you combine these components together, you can have the original signal. And we call this process, this formula, as a DTFT inverse of DTFT. Inverse. Alright, so this is a DTFT. This is definition and the meaning. But then we have a very good property of these DTFT. Actually, not just for DTFT. In some different class, you should know different courses. You should study the continuous times Fourier transform, the CTFT, right? They have the similar property. For DTFT, or we say just for Fourier transform, I have a table here. I have the properties. This one. Yeah, I have properties. Fourier transform zeros. Actually, they are properties, right? Let me make it large. Okay, it is this one. 6. You see, 6. This is one of the property of DTFT. Capital X times capital Y. This is in the omega, in the frequency domain. And this side is xn times yn, convolution with yn. This is the result we need to use to calculate the convolution. Yeah. So what is the meaning? So you have x is a signal. We can perform Fourier transform on this x. We get capital X, right? And we have another signal is a y of n. Then we perform DTFT. We have this capital Y. We want to calculate the convolution of x and y in time domain is a convolution. Now we times these two together. Okay, so this calculation is easy, right? You just times them together. You do not need to convolution. Convolution, you have a lot of things you need, a lot of multiplication and a lot of summation, a lot of calculation. But here you just do a multiplication. You times these two together. Okay, after you times these together, you go back to time domain. You can have the result. So you know what is the convolution of xn and yn. So this gives us a way to calculate convolution. It's a shortcut, right? So find convolution by Fourier transform, DTFT. So x of n by DTFT, we can have capital X e to the j omega, and the y of n, we also perform DTFT. We have y of e to the j omega. Then we times these two together. We have x e to the j omega, y of e to the j omega, and then we perform the inverse DTFT. This is just the x of n convolution with y of n. So we can find the convolution between x and y by this way. In this way, we do not need to do the convolution actually, right? We do a transform, do two transforms, Fourier transforms, then times them together, and then an inverse transform. So we need two Fourier transform with one inverse Fourier transform, and just one operation. This is times multiplication, right? Then we have this result. Okay, so this gives us a very easy way to find the convolution. Okay, then we can use an example to explain it. I have x of n. For example, this is 1/2 to the n times u of n, and y of n is 1/3 to the n u of n. I have two signals. Yeah, you can see the first one for negative n's, it is 0 because I have u here. So for negative n, the value must be 0. U of negative n is 0. And for positive n, when n is 0, it is 1. Then 1/2, 1/4, 1/8, right? And so on. Smaller and smaller. And this one is similar. 1, then 1/3, or even I can put 2, some larger. 2/3, then 4 of 9ths, then 8 of 18ths, and so on. Yeah, similar thing, but this 1/2 going down faster and 2/3 going down slower. It looks like this. Now what is a convolution of x and y? What is the convolution of these two signals? Okay, now we solve it by this way. X of e to the j omega, which is a DTFT of x of n, equal to, I will perform DTFT on it. Oh, people will say, okay, you need if you start from the definition to find it, there will be a lot of work. Okay, we have another table. Here we have another table. Actually, I have 3 tables for the Fourier transform, and you can use it. These tables I already posted in Blackboard, and you can also find them from the textbook. I just print them from textbook and then post to the Blackboard for your convenience. Every time you search on your book, you can also just go to Blackboard. You find these 3 tables. You can also download these tables from Blackboard to your computer. Then you have them, right? The convenience for you. If you search online, just the DTFT tables, you can find a lot. Now you can also use any tables from the internet. Yeah, but similar thing. Maybe a small different. Okay, now we have this term. You can see the first one, a to the n times u of n, and a is a number smaller than 1. Absolute value is smaller than 1. And in our example, the a equal to 1/2 and 1/3, right? So okay, so we can apply this term, the fourth row. This is in time domain, in n domain. Then we go to the omega domain, is 1/1 minus a times e to the negative j omega. Okay, let me copy this. It is 1/1 minus a. A now is 1/2, right? 1/2 e to the negative j omega. Alright? Yeah, it's here. Alright? So x is this one, just by table. And the second one, y, second signal, we still use by DTFT, we can have 1/1 minus, now is 2/3. Right, second one, this a is 2/3. 2/3 e to the negative j omega. Right, still by table. Right, so we have these. Okay, then we have x e to the j omega times y of e to the j omega equal to, you just times the two together, is 1 minus 1/2 e to the negative j omega and 1 minus 2/3 e to the negative j omega. This denominator. Numerator is just 1. Alright, so we just times them together. And then we want to go back, right? We want the inverse. We still want we can have the help from the table. So let's go back to the table. Go back to the table. Okay, so this is the table. Table Fourier transform pairs. One row, this side, this column, one column, this column, they are signals, and these columns are functioning as in the frequency domain. So now we want to find, do we have that term here? It is 1 over 2 factors. Can I, like this? Yeah. Yeah, we want to find, can we find these from the table? If we can find it, that will be good, right? But unfortunately, I will say no. You see? Do we have? No. We don't have. We don't have like 2 factor times together, right? Oh, this one may be a little bit looks like similar, but I think it's not. This is more complex, right? We don't have. I will say I don't have. We only have this one. 1 over, you see, 1 minus a. You just one factor, right? I have 2 factor in denominator, but in the table we have only have terms looks like this. Okay, so here we need to do something before we use the table. Actually, you have 2 choices. One choice is by the definition. By definition, you have what is a capital X, right? You go to like here. I have this one. This is definition, right? We want go back to find this x. Then we calculate this integration. It is a capital X times e to the j omega n. Now is a x convolution y, so I can use this. I say x of n convolution with y of n. Oh, yeah. X of n convolution y of n will equal to 1 over 2 pi, the integration of one cycle to 0 to 2 pi. Then this one, capital X e to the j omega times y of e to the j omega, then e to the j omega n, the d omega. Now you can calculate this. You can calculate this. But unfortunately, this is also a long calculation. Yeah, you can do it. You can do it, and finally you can have the result, but it's not good. It is good, but it is hard. You see, I'm sorry. Yeah, it is good, but if you can calculate, but it is hard. So we still want to use the table. We still want to use the table. Yeah, we still want to use the table. Then we need to make some change here. This part, we want to write these in terms of this one. You got it? So now try to rewrite. I say this is 1 as 1 minus 1/2 e to the negative j omega, and plus another 1 minus 2/3 e to negative j omega. Here's A, here's B. Yeah, we try to write it in this way. Of course, we have a problem. Can we do it? Can we do it? Okay, the thing is, just let this one equal to this one, and you can solve A and B, then it works, right? Right. Okay. I think, yeah, some of you guys, if you have some other course, you have similar method, you should know this is a method called a partial fraction method, right? Partial fraction. partial fraction. So this is a one fraction, somehow complex, and you try to write it in terms as a summation of some simple terms, simple fractions. Okay? Each is we call it a part of it, right? It's a partial fraction. Can we do it? Okay. Okay, this one, right? We want this one equal to this one, so we want this one. Let me copy it, and okay, we want this one equal to, so we want this one equal to 1 minus 1/2 e to the negative j omega plus b over 1 minus 2/3 e to the negative j omega. Okay, we want this for certain a and b. Of course, you cannot put any a and b here. We try to find some special value so that these two sides equal. So this is equation, right? This is equation with two unknowns. One equation with two unknowns. But actually it is not one equation because omega is a variable, right? Omega is a variable. You put different value of omega, this gives you different equation. So this one exactly gives us like infinite equations. You want to solve a and b, no problem. Yeah, we can solve it, right? We can solve like this. We times 1 minus 1/2 e to the negative j omega and 1 minus 2/3 e to negative j omega on both sides. I times this denominator on both sides. By this way, we can have equation without a fraction. Right? Now this is a fraction. This equation with fractions. So we remove the fraction. We times the denominator, the largest denominator on both sides. Then we have 1 equal to, okay, this is a still a, and this one times this one. Then I have 1 minus 1/2, 1 minus 1/2. So these two cancel. So we only have 1 minus 2/3 e to the negative j omega and plus b times, okay, these two cancel, right? 2/3 terms cancel, and we only have this 1/2 term left. So here's a 1 minus 1/2 e to the negative j omega. So we have this. Alright, so this is 1 equal to a minus 2/3 e to the negative j omega a plus b minus 1/2 e to the negative j omega b. We have these, and these three, they are constant, and this one and this one, they are functions. They are functions, right? Functions of omega, and both sides should be same. So we know constant were equal to constant, and function omega were equal to, alright, this side we do not have function of omega, so there will be 0 equal to, that is a negative 2/3 e to negative j omega a minus 1/2 e to negative j omega b. So we have these two. Now I see we separated the one equation. Now I have two equations, right? Two equations. The two equations, the first one just for number. Second term, I have a function here, but I can erase it, right? I divide it by e to the negative j omega, then give us 0 equal to negative 2/3 a minus 1/2 b. Alright, so we have these two. I say this is 1. I already used 1, right? This is 2. This is 3. So I can solve a and b from 2 and 3. Give us what? Give us a equal to 1 minus b right? A equal to 1 minus B, and plugging here, I have 0 equal to negative 2/3. A is 1 minus B minus half B. So this is negative 2/3 plus 2/3 B and minus 1/2 B. And this is a negative 2/3 plus, this is 2/3 minus half B. It is, okay, I move 2/3 this side, right? Negative 2/3 to the left, and right side is 2/3 minus half is what? Is a 6 times 6. This is 2 times 2 minus 1 times 3, and B. So this is a 2 2 is 4. 4 minus 3 is 1. 1 6 B. So B is what? I times 6 on both sides. Right? So this is 4. I got B is 4. B is 4. B is 4, then A is 1 minus B will be negative 3. Negative 3. Okay. Now we have this one equal to A is negative 3 of these, and the B is 4 of these. Okay. And actually this part is what? This is capital X right here. Capital X times capital Y. Capital X times capital Y is equal to A is negative 3 over 1 minus 1/2 E to the negative J omega, and B is 4 over 1 minus 2/3 E to the negative J omega. Now we have this one. Alright, then we can use the table. We can use the table, right? We already know those two terms on table, right? So we have in time domain, this is by DTFT to the inverse. I have x of n convolution y of n, right? These two, you go back to time domain will be convolution, and then these two go back. It is negative 3 times 1/2 to the n u of n, and am I good? This is a 2, this is a negative cancel, yeah. This one, and plus 4 times 2/3 to the n u of n. Okay, we got it. That's it. So we have the convolution. It is this one. It is this one. Is this simple than direct calculation? I think it is simple. In the direct calculation, you need there's a summation with infinite terms. So you always get something confused, right? But now we use this way. We times that two together. We times them together, then do the partial fraction. Then we solve these equations. We find A and B. Then go back by the table. We get it. So in most cases, this will be simpler. All right. So by this way, we can calculate the convolution. All right. Okay. Now, before we keep going on, we can study more about the Fourier transform, because Fourier transform it contains more material, not just for convolution. We have more information. So let's go back to the table. I have three tables here. The first table, it lists here's 11 signals and their Fourier transform. These signals are common used signal in the signal processing. You can go over it. Like here, first one is DART, the impulse signal. The second is still impulse but shifted. And the third one is one forever. And they put this U in the 5. U is the fifth. So third term and the fifth term, they are similar. Third one is 1 forever. All the ends is 1. And the fifth we only have one for positive ends. Negative ends it is 0. And then in after the Fourier transform, we have these two. You see, both they have infinite summation of dirt, right? This is a summation of all the dirt plus the delta of omega plus 2 pi k. Let me show you. It's right here. DTFT. Here I want to know what is the dirt of omega plus 2k pi. What is this one? This one is an impulse. It is an impulse. And this point is this is omega. Omega equal to negative 2 pi k. So if k is positive, if k is negative, you have this point. If k is positive, the pulse will be here. So this one is an impulse. The pulse happen at omega equal to 2 pi k, negative 2 pi k. Alright. And 1, we do DTFT. We have a summation of 2 pi dirt omega plus 2 pi k. K run from negative to positive infinite. This is a in omega domain, right? Frequency domain. For omega equal to all the 2 pi k. So I have 0 when k is 0. Then here's a k equal to negative 1. Right? This is 2 pi. So every 2 pi we have an impulse. Here's a k equal to 1 is here. Alright, delta is the 2 pi dirt. It's a 2 pi times dirt. 2 pi dirt. Alright, so this is a DTFT of 1. And the DTFT of U of n, this one, we still have summation, but now is pi times dirt, omega plus 2 pi k. Right? This is pi, not 2 pi. And the k still run from negative to positive infinity. This is interesting. 1, you get 2k pi. And this one is you also have the parts. Similar thing, right? Just the pi. This is the pi dirt. So half of it. In time domain, it is this is 1 forever, right? 1 half forever, and this is half. We only have this side. We have 1. This side is 0. This is in time domain. This is in time domain. And when you do this is in time domain. This is U is half of 1. The 1 is 1 forever. U is 1 only for positive n. Then go to the frequency domain. The 1, according to the Fourier transform, it looks like this. We have sequence of parts. The sequence, the impulse is the 2 pi dirt. Now this one is only pi dirt, half. This is so here's a half end, and here's half. All the peak value is half. But not just this. You need a plus 1 over 1 minus e to the negative j omega. Yeah, we have one more term. So this one, it is half of these plus this one. When you perform plus this one plus this, right? Plus this. Yeah, the table is here. Right? Table is here. Yeah. Okay, we have more. Actually, we have totally 11 terms, and let me see which part will be important. So I suggest you go over the table. Totally 11s. You go over them one by one. You use computer to give graph of each side. This side you use dirt, right? You use stem of something. And this side you need like omega run from, you check if you want you can check 2 cycle, like from negative 3 pi 3 cycle to positive 3 pi, and use a MATLAB command. There will be negative 3 pi with a step. One step is a 0.01 for example, then to 3 pi, and then the capital X or equal to you check the formula, right? Different signal, you have different formula here. You get this formula from the table, then you type these, then you plot. But this X is a complex number, so you need to plot these, use like a real X or imaginary X or the magnitude X, the ABS X, and plot the angle of X, the A, lowercase a, and the angle of X. You use these two to plot them. You go over all these signals. Then you can have a sense about them. When you look at the formula, you know, okay, how do they look like? Not just the formula. You look at the formula, maybe you can remember it, but usually, in my experiment, usually you will forget it after a few days. You remember it after a few days, you forgot it. Yeah, you have no sense. But if you give a graph of them, you can have a sense about it. Then you can remember more for more times. This is one table. I have another table. Yeah, this table is the properties theorems, the Fourier transform theorems. They give us the way to calculate. You see, like if you have a combine of 2 signals in frequency in time domain, then in the frequency domain you can have the same combination, and you have a shift in the time domain, then you multiply exponential power in the frequency domain, and so on. So I also suggest you do similar thing. You go over all these terms. Totally we have 9 different properties, 9 different zeros. You can think. You go over them. This time you do not need to use computer. You need to use brain. You look at them, think about it, and try to understand the meaning of both sides. What are these one? What are this one and this one? Right. So peer and the peer. Try to understand them. All right. And if you have any doubt, you can go to the office hour, or you can leave your question in the piazza. Try to understand all of these, and later we will use them. This is second thing. And the third thing, this is also similar with the theorems. This is a symmetric properties of Fourier transform. So there are totally 13 different terms, and each term according to the kind of change of the signal, like x of n. If we change it to be a x conjugate of n, then what will happen in the frequency domain? All right. This part I think I need to give some explanation. So next time I can let's keep working on this one. All right. Okay, that's all for today. So see you next time. See you next week. Right? This is Friday. So okay. Bye bye. Have a good weekend.